Okay, let's talk about electronegativity and bonding. So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. So essentially it's the pull it has on the electrons that are being shared. Okay, um, so with this, that pull that it has actually results in what we would call polar, nonpolar, and ionic bonds. So really what we're talking about is covalent bonds and ionic bonds, but covalent bonds can be either polar or nonpolar, depending on if you have an atom that has a stronger pull on the electrons than the other in that particular compound. Now, this is actually inversely related to the atomic size. And so if you have a smaller atom, it actually is going to have a stronger pull on the electrons. And that's because in a smaller atom, the electrons are closer to the nucleus. Okay, and the nucleus is where there's the positive charge. And that's really what's attracting those electrons to the atom. So when you have smaller atoms, those electrons are closer to that positive pull in the nucleus. Whereas larger atoms, they can't quite feel that positive nucleus as much. Even though there's more positive charge in there, those electrons are further away from that nucleus, and they just can't feel that pull as much. And so those larger atoms have a smaller electronegativity. Now you can relate all of this to the periodic table. There's kind of a general trend that electronegativity follows. So if you look at the periodic table, as you go towards the right-hand side of the periodic table, the atoms actually are smaller. Okay, as you go from left to right across the periodic table, your atoms get smaller. Thus, your electronegativity increases as you go from left to right across the periodic table. And then as you go from the bottom to the top of the periodic table, your atoms also get smaller. That would be because of less shells of electrons on those atoms. And so your electronegativity also increases. Or you can look at it the other way. You can say from right to left, your atoms get larger, so your electronegativity decreases, or from top to bottom, your atoms get larger, so your electronegativity decreases. So whichever way you want to think about it, if you want to think about it in terms of larger or smaller atoms, if you're thinking about smaller atoms, your electronegativity has got to be increasing, and larger atoms, your electronegativity is decreasing. So you can always look at the periodic table and get a general idea of how one element's electronegativity relates to another. Now this is a general trend, so it's not perfect. It works pretty well for main group elements, but the transition metals, it's not as strong of a trend. It's not as easily predictable. So you'd usually use this and apply it to most main group elements. So if something's further to the right or higher up in the periodic table, you would generally assume the electronegativity is larger. Now, sometimes you'll work with actual electronegativity values. Okay, so numeric values associated with the electronegativity. Those aren't things that typically someone would expect that you memorize. It's just something that you can look up or maybe is reported to you and expected to be able to be used. So I've got a table here or a diagram that gives you electronegativity values of different elements. Now this one only gives you one decimal place. You can find other resources that give you more accurate electronegativity values. And also the values will vary from others just based on what technique they use to determine the electronegativity. So there's a couple different ways it can be, looked at and determined. But the constant for electronegativity is that fluorine is assigned a value of 4, okay, or 4.0. Fluorine is the element that has the highest electronegativity, meaning your atoms of fluorine have the strongest pull on electrons. Although fluorine's not actually going to be necessarily the smallest atom, because you've also got hydrogen and helium. Those are pretty small atoms, but they don't generally want to pull electrons towards them, because they don't have room to hang on to many electrons anyway. So fluorine has the highest electronegativity, and then it decreases as you go towards the bottom left on the periodic table. But as I said, it's not perfect, and if you look at the transition metal area, you'll notice some fluctuation in that going up and down, and so you generally think of that general trend, the general periodic trend, relative to the main group elements. So you can look up these values. You can utilize these values to understand what type of bond is being formed between two elements. And so let's talk about that. And so that we would generally refer to as bond polarity. And so bond polarity is going to depend on the electronegativity difference between the bonding elements, okay? And so there's kind of 3 layers of this, okay? So you can have what we would call a nonpolar covalent bond. That would be when the 2 elements that are bonding have either no difference in electronegativity or a very small difference, okay? And so no difference could be because you actually have 2 atoms of the same element bonded together. That for sure, if it's the same element, it's the same electronegativity, so it's definitely a nonpolar covalent bond. But there are some elements that have very similar electronegativities, so when they bond, they can form a nonpolar covalent bond. Generally, the only way that you would know that for sure is by looking up the electronegativity values and seeing, is the difference somewhere from 0 to 0.4. Now, one that people would usually assume is going to form a nonpolar covalent bond is when you have carbon and hydrogen linked together, because their electronegativities are very close to one another. And we deal with a lot of compounds that involve carbon and hydrogen bonds. Those would be organic compounds, and those, if you just have carbon and hydrogen bonded, all of the bonds are nonpolar, and it's a nonpolar compound then. But any other like elements bonded together, so if you have, say, a Cl2 molecule, well, if you looked up the electronegativity of chlorine, it's 3.2, and both of them would have that same electronegativity, so if you subtracted them, you get 0. And when you look at the difference, you should always look at the absolute value. So it doesn't matter which way you do the subtraction. If you come out with a negative, you just drop that negative. And you're looking at the range. So if that range is small, something less than 0.4, it is considered a nonpolar covalent bond. So even though there could be a little bit of a difference in electronegativity, meaning the share isn't perfectly equal, it's close enough that we consider them shared equally. Now, you can also have polar covalent bonds, and polar covalent is going to be some sort of intermediate difference in electronegativity. And usually we define that something from 0.4 to 2. Okay, so if the difference is somewhere in that range of 0.4 to 2, then we'd consider it a polar covalent bond. So they are sharing electrons, that's why it's a covalent bond, but it's polar, indicating that it's not equal, and so it's heavier on one side than the other, or it's more positive and on one side and more negative on the other. Okay, so there's this unequal sharing in a polar covalent bond. So for instance, if you had hydrogen bonded to chlorine, that does form a covalent bond, but chlorine has a significantly larger electronegativity than hydrogen. And so what happens is it does not share the electrons equally. The chlorine will pull the electrons more towards it. And so the hydrogen will be kind of lacking in the electrons. It won't have as much access to those shared electrons as the chlorine does. And so the hydrogen end of HCl will have kind of a slight positive charge, whereas the chlorine end will have a slight negative charge because it's pulling extra electrons towards it. So anything with a difference in electronegativity somewhere between 0.4 and 2 would be considered a polar covalent bond. Now the last one is an ionic bond. So an ionic bond, remember, is when electrons are completely transferred from one thing to the other. Okay, so this is actually when you have such a large electronegativity difference that one of those atoms actually has such a great pull on the electrons, it just completely takes the electrons. And so that's going to happen when the electronegativity difference is greater than 2. Okay, so if it's greater than 2 of a difference, then whatever has that larger electronegativity, it's just going to take the electrons from the other element. And the other element's going to be kind of okay with that. And so this is going to form ionic bonds because it'll form ions and those ions will be attracted to one another. And so this happens, for instance, in NaCl. Okay, so if you look up the electronegativity of sodium, you'll see that it's 0.9. And if you look up chlorine, it's 3.2. So if you subtract those, again, like I said, it doesn't matter which direction you do the subtraction, just so you then drop the negative if it comes out negative. And so in this case, it came out to 2.3, so it came out greater than 2, indicating there's a significant unequal sharing, so much so that really it's not even sharing. The chlorine's just taking those electrons, whereas the sodium is letting it, and so then it forms a cation and an anion, and they then are attracted by way of an electrostatic attraction, which we call an ionic bond. Okay, so this is kind of your extremes of bond polarity. You can have nonpolar where it's completely equal sharing, whereas you can then have ionic, which is the other end of the spectrum where it's not really sharing at all. And then you can have that in between where it's polar. It's sharing, but not really